Hey, welcome. Have you ever heard that word algorithm and just kind of pictured some super complex sci-fi computer brain? Well, today we're going to pull back the curtain on all that. We're going to show you that yes, you probably use algorithms every single day. In fact, you might use one to solve your next hunger crisis.
So, let's start with a really important problem. You're hungry. You want pizza. What's the plan? You probably have a little checklist in your head, right? You got to pick a place, choose your toppings, use an app or call them up, give them your address, and then just wait for that cheesy goodness to arrive. Well, that step-by-step plan you just made, that's everything.
Because that's literally what an algorithm is. It's not magic, it's just a recipe. It's a clear set of simple instructions that you follow to solve a problem. And it doesn't matter if that problem is figuring out a rocket's flight path or, getting a pizza to your door.
And that is the key takeaway here. These recipes aren't just for computers. They are these fundamental problem-solving tools we use for almost everything.
I mean, just look at this list. On one end, you've got your GPS finding the fastest route home. That's a super complex algorithm chewing through tons of traffic data. But then on the other end, you have the simple steps to make a cup of coffee. They're all the same basic idea, though. They're all a set of instructions that take an input, like I'm lost or I'm tired, and give you an output, like directions to your house or a nice hot cup of coffee.
Okay, so how do we take an everyday recipe and turn it into something a computer can actually get? We have to look at the anatomy of a more formal, a digital recipe. See, a computer can't guess what you mean. Every single step has to be perfectly clear.
To write an algorithm for a computer, you have to be incredibly precise. Before you even write the first instruction, you have to formally define the problem. It's kind of like setting up your kitchen, getting all your ingredients and tools out on the counter before you start cooking. And these components, they map perfectly to our cooking analogy. The givens, those are your inputs. That's your flour, your sugar, your eggs. The results, that's the desired output. That's the delicious cake you want at the end. And the method, well, that's the actual recipe, the step-by-step instructions that turn those ingredients into that cake.
All right, let's put this into practice with a classic computer science problem, just adding three numbers together. I know it seems really simple, but laying it out this way is exactly how programmers make sure their code is clear, predictable, and does what it's supposed to do.
So here's what the method looks like. The get commands, that's like asking the user for our ingredients, the three numbers. The let command, that's the main instruction. That's where the actual cooking, the addition, happens. We store the result in a little container we call total. And finally, the give command serves up the dish. It presents that final total as our output. Simple, clear, and zero guesswork.
Now, that was a pretty simple recipe. But what happens when the problem gets bigger? What if instead of ordering one pizza, you had to coordinate deliveries for an entire city? For almost any problem out there, there's not just one recipe. There can be dozens, even hundreds of them.
And that brings us to the biggest question in algorithm design. If you have all these different recipes that all make the same cake, which one do you choose? Is it the one that's easiest to read? The one that's fastest? The one that uses the least amount of memory? This choice can be the difference between a website that loads in a blink and one that makes you want to throw your laptop out the window.
We can pretty much boil it down to two main things. On the left, you've got clarity. Is the recipe easy for another person to understand? Super important when you're working on a team. But for this explainer, we are going to laser focus on the right side, performance. How fast does it run? Because in the digital world where every millisecond counts, efficiency is king.
But here's the twist. An algorithm's speed isn't always the same. It's kind of like looking for your keys. It might take you 1 second if they're right there on the hook by the door, or it could take 10 minutes if they're buried under the sofa cushions. An algorithm's performance can change, a lot, depending on the specific problem you give it.
So to see this in action, let's use a really simple algorithm called a linear search. The goal is super easy. We just want to know if the number 3 is inside a list of other numbers. And the method is as simple as it sounds. You start at the beginning of the list and you check each number one by one. All right, here's our first list. We're on the hunt for the number 3. See it? Yep, it's right there at the very beginning. So what do you think happens when our algorithm gets to work?
Bam, one comparison. We find it on the very first try. This is what computer scientists call the best case scenario. I mean, the algorithm barely broke a sweat. It's the absolute luckiest you can get.
Okay, now for a totally different list, take a close look. Our target, the number 3, it's just not there. But remember, the algorithm doesn't know that yet. So, what does it have to do?
Well, it has to check the first number, nope. The second, nope. The third, the fourth, it has to go all the way to the very end of the list. After 12 comparisons, it finally gives up and says the number isn't there. This is the worst-case scenario, where it had to do the absolute maximum amount of work possible.
So this idea of a best case versus a worst case is absolutely crucial. And the way computer scientists formally measure this huge difference is by meticulously counting every single basic operation an algorithm has to perform.
And this whole process has a name. It's called algorithm analysis. It's all about predicting how much time or memory an algorithm is going to need. And we usually focus on that worst-case scenario because, you know what? It's a guarantee. It tells us the absolute longest this thing could ever possibly take, no matter how unlucky we are.
So how do we actually do this analysis? Well, one of the most fundamental techniques is something called tracing. It's basically where you grab a piece of paper and a pencil and you pretend to be the computer. You go through each instruction one by one, and you keep track of everything that changes.
Okay, let's trace an algorithm that finds the average of 3 numbers. Look at the table. On line 1, the first instruction runs, and our variable num1 gets the value 24. Line 2, the next instruction runs, and num2 becomes 31. Line 3, num3 becomes 35. Now, line 4, we do something. We add those 3 numbers up, and the result, 90, gets stored in sum. Finally, line 5, we do another operation, a division, and we store that result, 30, in AV. By stepping through it just like this, we can count every single step and analyze how efficient this recipe really is.
And this all brings us back to that big question. Why does any of this matter? Because behind every social media feed that loads in an instant, and every GPS that reroutes you without you even noticing, there was a programmer who was obsessed with finding the most efficient recipe. A better algorithm means a faster, smoother, and just plain better experience for all of us.
So I'll just leave you with this thought. The next time you search for something online and the results appear in a fraction of a second, or your photo app instantly tags a face in a picture, just take a second to think about that elegant, efficient, and totally invisible recipe that made it all happen.